So we're going to do the same thing that we did for the spring. We're going to do the same thing for a pendulum. And it's going to be the same general format, but instead of using the M and K that we used for our spring, we're going to use the factors that affect the period for a pendulum. So we have T and then the P for period. Same general format, so 2 pi and then the square root, and this will be L over G. Okay, where T is the period of the pendulum. In seconds. L is the length of the pendulum. So that's the length of the string measured in meters. And then G is going to be our acceleration due to gravity. In meters per second squared, and that's our 9.8. And we're going to have our same general format for our angular velocity. So in our angular velocity, we had switched around our letters. If we look over here in the yesterday's work, we had our period was m divided by k. So our angular velocity is going to be the inverse of that, k divided by m, because again, we're looking at that inverse relationship. Okay, so angular velocity is going to be the square root of g divided by L, and you can do capital L or lowercase. I've seen both. So, angular frequency, which is going to be in seconds to the negative 1. Then we have again the length of pendulum in meters, and our acceleration due to gravity. Okay, so the question is asking, what must the length of a simple pendulum for a clock, which has a period of 2 seconds? So the length is what we're looking for. The period is going to be 2 seconds. And of course we know G is 9.8 meters per second squared. So period equals 2 pi square root of L over G. So to rearrange this formula, this is a weird one to rearrange. First thing we're going to do is divide both sides by 2 pi. So we end up with T divided by 2 pi equals the square root of L over G. And then we want to square both sides as well, so we can get rid of that square root. So when we do that, we get T squared over 2 pi equals L divided by G. And this is 2 pi squared. And you can distribute that square out or leave it however you prefer to work it. Okay, and then we are looking for the length. So from there we're going to multiply our G up. So this is T squared times G divided by, and I'm going to go ahead and distribute this, 4 pi squared will equal our length. So we're going to plug that in. So our T squared, so that's 2 squared times G, 9.8, divided by 4 pi squared. And when you type this into your calculator, you want to make sure that you are putting this bottom 4 pi squared in parentheses, because otherwise it's going to give you the wrong answer. So you do 2 squared times 9.8, and then you're going to divide that parenthesis, 4 pi squared. You can also realize that 2 squared is 4, so these two are going to cancel out. So when we plug that in, we get 0.993 meters. So our string needs to be about a meter long to get a period of 2 seconds. Now we can always look at the formula to see what affects the period of our spring mass oscillator or our pendulum. And things that we need to see that don't matter. In a spring mass, the amplitude does not affect how long the period is. So if I pull the mass down farther, that doesn't actually change the length of my period. The only thing that affects it is the mass and the spring constant. And for a period of the pendulum, you would think it affects it, but it really doesn't. This is going to be the mass of the pendulum itself. So even if you increase the mass that's on the end of your string, it doesn't affect your period. Because we can see up here, the only thing that affects it is the length and acceleration due to gravity. We can easily change the length, but to change acceleration due to gravity, you'd have to actually take it to an entirely different planet. And so the only way that we can change how long a pendulum works, or how long it goes between oscillations, is by changing the length. So the next couple examples are going to be looking at the relationship within the formulas. And this is important because these are questions that they ask a lot on the AP exam. If I double this, what happens? And different things like that. So we're going to start with a spring mass, and then the second problem we'll talk about a simple pendulum. So consider a spring mass oscillator whose period is t. Determine the new period in terms of t for each of the following cases. So the formula that we're going to be using and studying the relationships between is the period of our spring. So 2 pi square root of m divided by k. Okay, so if we double the mass, that's underneath the square root. So what's going to happen to our t is it's going to be multiplied by the square root of 2. So same sign because they're both on top, but under the square root because the mass is under the square root. If we doubled our spring constant, that's on the bottom, so we have the opposite sign, so we're going to divide, and then it's 2 and the square root of that. And again, you can always plug in fake numbers, but remember that we want to leave it in terms of t. So because of the square root, it's a whole lot easier to just leave it in terms of that square root and look at your formula and do it that way. If we double the amplitude, remember that the spring period does not depend on amplitude, and it's nowhere in our formula. Okay, so this will have no change. So if we wanted to know what our new period is, it's just t. So if we want to double the period, okay, so period is doubled, what must be done to the mass? So now we want to work backwards, okay? So we can alter our formula and look at it that way. So t squared equals 2 pi m, oh, that's 2 pi squared. This is just taking the square root and moving it, m divided by k. So if I want to double this, I would need to quadruple my mass, because whatever the square root of whatever I do to the mass is going to be square rooted. So in order to double this, I need the square root of 4. So times the square root of 4, and the square root of 4 is going to be multiplying by 4. And we can do the same thing with the spring constant. Okay, so here if I doubled this, my mass was increased by 4. So if I do the same thing, use the same formula, 2 pi squared, we'll do it that way, m divided by k. if I double the period, then the K, I have the opposite sign, and then I square the number. So you can look at this a couple different ways. You can work backwards here and know, well, if I multiplied by 2, I took the square root of 2. So in order to get this to be 4, I have to square that. Or you can change your formula to where your mass is just on the outside like a normal variable and look at that squared relationship there. So we're going to do the same thing for a pendulum. We want to write down our new formula that we're looking at. And that's an L, not a 4. Exaggerate that. There we go. So if we double the length, again, to the period, because we're determining the period, is now going to be multiplied by the square root of whatever we did. So again, square root of 2. Okay, now this one is interesting. This refers back to the previous unit, and you're going to have to do this a lot. So the pendulum is taken back to a planet whose mass and radius are twice as much as Earth. So we've taken the mass of the planet and doubled it. We've taken the radius of the planet and we've doubled it. And if you remember back to our formula in the previous unit, we determined that to find the acceleration due to gravity on a planet, we take g times the mass of the planet divided by the radius squared. And that was derived from our universal gravity constant. So if I double my mass, I'm going to double my acceleration due to gravity. If I double my r, because it's on the bottom, I'm going to divide by whatever's done to r squared. So 2 squared, which is 4. And if I combine those things, the total amount that I'm changing g is I am dividing it by 2. That's just what's happening to my acceleration due to gravity. So now if I refer back up here to my formula, g is on the bottom, t is on the top on the opposite side, so I do the opposite sign. So now I'm not dividing, now I'm multiplying. And it's going to be the square root of whatever the number is. So the square root of what I do to g, which would be the square root of 2. And you're going to need to make that jump and use that formula if I ask you a question like this. You need to be able to make that connection. Okay. Okay, so a few more example problems and then we'll be done for today. This is an object has a mass of 3 kilograms and oscillates at the end of a spring and has a position described as a function by time of this. Now remember, we already did this one, okay? Where x is in meters, t is in seconds, determine the following. So, first question is the amplitude, and if we remember our formula, it was x equals a cosine then 2 pi ft, or remember that we could replace this part with w, so a cosine angular frequency times t. Okay, so the first thing is the amplitude, and amplitude is going to be this first part. Okay, today I wanted to start by pointing out something that you may not have realized yesterday. We know from our previous unit that period and frequency are inversely related. Okay, I wanted to talk about something that you may not have noticed yesterday, and I didn't point out either. I wanted to talk about period and angular frequency and their relationship between the two. So remember from our previous unit on circular motion that period and frequency are inversely related. That accounts for why the inside of our square root is flipped. And then when we get into angular, that has to do with our circle, and so that's why the 2 pi disappears. Now there's more to that equation, but for now, that's what you need to remember. And we know that our angular frequency also equals 2 pi times our normal frequency. So let's continue on with our discussion of the simple pendulum today. And we're going to do all the same formulas that we did before, but now using the different variables that affect a simple pendulum. So we have the same general format for our period. And again, both of these are on your AP reference chart. The subscript tells you which one's a spring and which one's a period. So, or pendulum. So you don't have to memorize these two. I know whenever I go back, I always flip what's underneath the square root. So I would always double check with your equation chart which one you're doing. So this is going to be an L over G. And lowercase or uppercase is fine on the L. It doesn't really matter. So then we have the period of the pendulum in seconds. L is going to be the length of pendulum in seconds. And then G is going to be our acceleration due to gravity. And that's meters per second squared. And that's our standard G variable on that one. So then we can do the same thing that we did with our the spring mass oscillator. We can do with our angular frequency. So we're going to take just the inverse of what's inside. So this will be G divided by L. So here we have angular frequency, seconds to the negative 1, and we have the length of pendulum in meters, and then acceleration due to gravity, meters per second squared. So, this next question, it says, what must the length of a simple pendulum be for a clock that has a period of 2 seconds? So we want to know the length. We know the period is 2 seconds. And we also know that G is 9.8. Remember, you don't have to always write that down. Just thought I'd be thorough. So the formula that we're going to use is this one here. And since this is kind of an odd formula to rearrange, we're going to go ahead and rearrange this one together because it's kind of odd. So we're looking for the period. So the first thing we want to do is move the 2 pi over and get rid of the square root. Okay, so we're going to divide by 2 pi, and then we're going to square both sides. And so that square gets rid of the square root. And still looking for period. So I'm going to go ahead and distribute the square. And I'm going to move the G over. So again, 2 steps in 1. Okay, so T squared times G, because I moved the G up, divided by 4 pi squared. And you want to make sure that you're being careful when you enter this into your calculator. So I'll show you how to do that in just a second. Let's go ahead and plug our numbers in. So 2 squared times 9.8 divided by 4 pi squared. So if you look, obviously the 2 squared and the 4 is going to cancel out. But just in case you didn't notice that, let's go ahead and enter it in like you normally would. So 2 squared times 9.8 divide. And you have 2 things on the bottom. Remember, your calculator doesn't recognize 4 pi as one number. So 4 times pi squared, close parentheses, and we get the length of our pendulum is about 1 meter long. So in order to get a period of 2 seconds on Earth, we have to have about 1 meter long amplitude. Or 1 meter long string. Some things that do not matter or do not affect the period that normally you would think logic dictates that it does, but it actually doesn't. On a spring mass oscillator, the period does not depend on the amplitude. Okay, so no matter how far you pull back that spring, it's not going to change how long it takes to go back and forth across that equilibrium point. And in a pendulum, the mass of the massive pendulum does not affect the length or the period of the pendulum. So in this example that we had right here, whether we had a 1 kilogram mass or a 20 kilogram mass, we're still going to get that same length. Now, this is, of course, we're ignoring air resistance and friction and all your resistive forces. Remember, we do ideal world. So, in an ideal world, these things don't matter. And in the experiments that you do, you're going to see that they have very little effect on the actual period of that. So this next section is looking at the relationships, and it's going through that if I double this, what happens to all of those things, which are super important because the AP test is going to ask you to do that pretty often. So you need to be able to be practiced at this. And this is kind of a weird formula to do this with. So we're looking at a spring mass oscillator. So this is the formula we're looking for, and we want to leave it in terms of t. So am I doubling it? Is it being square rooted by some number? Like, what's happening to that period in terms of t? So I don't have numbers. I can make numbers, like make them up and do it that way, but that's not always going to give you the best option. So let's just go through this couple problems. Okay, so the first thing I want to do is look at if I double my mass. My mass is on the top, so whatever I do to mass, I'm going to do the same sign to period. So if I increase mass, I increase period. If I decrease mass, I decrease period. So I know that I'm at least going to multiply because they're directly related. Now the mass is under the square root, so whatever happens to mass, the square root of that happens to the period. So I'm going to multiply by the square root of 2. Now, spring constant is on the bottom, so if I double my spring constant, the opposite is going to happen to my period because it's on the bottom, so it's an inverse relationship. So I'm dividing or decreasing my period. Since it's under the square root, it's decreasing by the square root of whatever factor I'm changing my k. And then the amplitude, remember, is not in the equation and does not affect the period. So this will be no change. So your new period will just be t. Now for some of these, you got to go backwards. If I want to double the period, what do I have to do to the mass? Okay, so if I double the period, what's going to happen to the mass? So I know that the square root of whatever I do to the mass is what's done to period. So to get 2, to go backwards, same sign, I want 2 squared. So this is a square root, so to go backwards, I do a square. So I would have to quadruple the mass. So if I had a mass times 4, square root of 4 is 2. And then I can do the same thing with the spring. If I'm doubling the mass, I'm going to do the opposite to the spring constant. And then number-wise, I want to do whatever squared to the period I do to the spring constant. And so I need to divide that by 4. Okay, so now I want to do the same thing, but with a simple pendulum. So we're going to write down the formula that we're using, the relationships. Okay, so if I double the length, it's on top, so that's a direct relationship. Same, both are going to increase. and it's going to increase by a factor of the square root of 2 because my L is under the square root. Now this next one is a little bit different because it's telling us that we're taking to a different planet. So that means G is going to change. Okay, so that means the acceleration due to gravity is going to be different because we're on a different planet. And the mass and the radius are twice as much as Earth. So I'm doubling the mass of the planet and I'm doubling the radius of the planet. And we have to think back to our previous unit and remember that the formula for this was acceleration due to gravity equals gm over r squared. So that tells us that if we double our mass, our g is going to double. And if we double our radius, okay, it's on the bottom, so that's inverse. And there's a square, so we square the number. And when we combine those two effects to g, we end up that we are getting a smaller g. So we've decreased it by 2. Now that we know what happens to our acceleration due to gravity, we can go back and look at our period and figure out what happens. So g is on the bottom, so it's inverse, so we do the opposite sign. So if I decrease g, I increase t. And then because it's under the square root, I'm taking the square root of that number. And so it's going to be period times the square root of 2. Okay, the next couple examples are going to be something that we're not going to focus on, but I feel that you need to be exposed to. And it's using that position formula that we talked about. This formula is on your AP chart, but there really hasn't been a lot of talk about how important it's going to be or how much it's actually used. And I haven't seen very many released questions that actually use it, but I want to be thorough, so we want to go ahead and go through it anyways. And this is just some good math reasoning, which is always a good thing to practice anyways. So an object has a mass of 3 kilograms and oscillates on the end of a spring and has a position described by a function of time as this. So this would be like our graph, where x is in meters, t is in seconds, and then determine these 4 things. So the formula that we're using, just to kind of bring it back to your mind so you don't have to flip back and forth. And remember that this part here we can replace with our angular frequency. Okay, so those two things, remember, are the same. So the first thing that we want to do is look at our amplitude, and we can find our amplitude just straight from our equation. So that's going to be 7 meters. And we know it's meters because that's what this part was here. X is in meters. Then the next one asks us our angular frequency. So if we look at our formula, angular frequency is within the cosine, and it's multiplied by t. So that's this part here. So that would make this 4 pi. And of course we want to include second or unit, so seconds to the negative 1. So that's the stuff that we got from the equation. And we know from up here, so we're looking for period now, the angular frequency equals 2 pi times the frequency. And we know the frequency is equal to the inverse of our period. So that gives us this formula. So if we rearrange this one and this one to get period is 2 pi divided by our angular frequency, which is 2 pi divided by 4 pi. So the pi's cancel, and 2 divided by 4 is 1/2, so 0.5 seconds is going to be our period. Now to find frequency, we can do one of two things. We can either just take the inverse of our period, because that's what we know, that's how we got here to here. or we can use our angular frequency 2 pi f. Either one works. I'm going to go ahead and just take the inverse because it's a nice pretty number, and we can easily figure out that our frequency is going to be 2 seconds. So it's going to oscillate back and forth 1 cycle every 2 seconds. And that's seconds to the negative 1 because it's frequency. For this next part, we're going to actually have some new equations that I haven't actually given you yet. And they're not equations that I need you to know or to memorize, but you need to be exposed to them. So we're going to have the same thing again with our formula. We have 2 kilogram mass, spring going back and forth. Have our formula for our position. This time there's no pi, we just have numbers. And so we have x and t's and seconds, all the same stuff. So our formula tells us that A equals 5 meters, and that our angular frequency is 10 seconds to the negative 1. So it told us those things. To find the maximum velocity, you're going to take your amplitude and multiply it by your angular frequency. Okay, so we have 5 times 10 is going to give us a maximum velocity of 50. To find the maximum acceleration, again, these are just new equations, we're going to take the amplitude, maximum displacement, times the angular frequency times 2, or squared. And so when we plug that in, 5 times 10 squared, we end up with 500 meters per second squared. So those are the 2 new equations that you're going to need to find that maximum velocity and maximum acceleration. So that's the position, where the velocity is the maximum over the time it took to get there. And we're using the angular frequency because that has to do with that circular motion again. So these are, again, 2 equations you don't need to focus on, and I would not expect you to know how to do this problem other than the fact that we're working through it right now. Okay, so then for the spring constant, the only place that we have spring constant is either in our energy formula or our force formula. So we know that our force equals m times a and k equals kx. So if we're looking for k, we can rearrange and we can plug in. So problem told us a 2 kilogram mass. We solved a 500 acceleration, and that acceleration occurs at the maximum position, which we know is 5. So that's our amplitude. And when we solve that, we get a spring constant of 200 newtons per meters. The total energy, we can figure out the maximum spring energy when we're at the maximum stretch. So x is going to be that maximum position, and we know our k value. So u of spring is 1/2 kx squared, again using maximum position. And that'll give us the maximum energy of 2,500 joules. For these last 2 equations, it's going to be a little bit different. There's a lot of words, so you've got to go through and you got to read all of them. But it's really looking at, you got to look at what it's actually asking. So a pendulum is 1 meter long. So let's go ahead and write that down so that way we have our stuff as we go along. And is set into motion. The mass of the pendulum bob at 1 meter is 0.50 kilograms, and the period is calculated. So we get some period. The pendulum is set into motion, and the calculated period agrees with the measured period. So they ran an experiment. The bob is removed and replaced with a new bob. So mass of 0.25 kilograms. What is the new period of the pendulum? Okay, the question you have to ask yourself is what they changed was the mass. The mass does not affect the period. That means that the new period equals the old period. And all that mattered there was the length. So the period pendulum is 2 pi times the square root of L over G. So 2 pi times the square root of 1, and we're on Earth, so 9.8. That gives us a period of 2 seconds. So just because they changed the mass does not mean that the period changed. So we have the old period equals the new period. For this next question, we want to rank the different periods, or the different pendulums, in order from smallest to largest periods, or largest to smallest. So a student is given a set of pendulums. The lengths are 0.25, 0.75, 0.69, and 0.86. The student is asked to rank the pendulums in the order of their period from the greatest period to the smallest period. How should these pendulums be ranked if the student would like to be correct? So if we look at our formula again, all comes back to the formula and the relationships there. The larger the length is going to get you the larger period. So, if we want to rank them from greatest period to smallest period, we're going to do the longer one and the shorter one. So the longest measurement was 0.89 meters. The next one was 0.69, then 0.37, then 0.25. And that concludes it for today.